at the atom and the discovery of the atom. And we talked about the discovery of the subatomic particles. But one of the things that we really never talked about was what was really going on with the electrons. We know the protons and neutrons are in the nucleus of the atom. And we just said, hey, the electrons are out there somewhere. We said we'd address it a little bit later on. And this is a chapter in which we're going to address the electron. Now, when we start talking about the electrons, there are going to be some really interesting things that you are going to see in this class. There are going to be things that you're going to be like, wait a second, that sounds like spooky science. That doesn't sound quite right. And I'm going to tell you that you are technically in good company. Because as I start to go through some of these things and some of these implications of what's known as the quantum mechanical model, going into the quantum world, Einstein actually went to his deathbed not believing in some of the things that was coming out of the quantum mechanical model. And we're going to discuss about it. We'll watch videos. We'll look at some of the things that are actually taking place. Now, one of the things that Einstein thought that he did, he thought he found what was called the Achilles heel of this quantum world. And he was like, hey, I have found an experiment that is going to show that this quantum, this craziness, is not right. So he came up with this experiment. But the problem with the experiment is nobody could figure out how to actually do the experiment that he proposed. So he went to his deathbed and was like, hey, that experiment's going to once again disprove this thing. Later on, there was a graduate student who actually was able to look at the experiment that Einstein was proposing, came up with a way which actually to do the experiment, and what it did is it actually reaffirmed that the quantum model is actually correct. So we're going to talk about, once again, things such as the multiverse. And I can tell you that a long time ago, when I was teaching here at Visitation, and I would say, hey, you know what, there's this multiverse, and it comes out of this quantum concept, students kind of looked at me like, what are you talking about? Nowadays, it's a little bit easier, because there's like so many different movies out there, like, what is it, Spider-Man in the what? Exactly, in the multiverse. You also have Doctor, who is that? And he had also existed in the multiverses as well. So there's going to be a lot of things that come about. Way back in 2003, when this thing kind of really started, playing out, like some of the things with regards to the multiverse. And this was, once again, before you were born. I remember showing this article to students, and it simply says on the cover of Discovery, this magazine, that if the electron can be in two places, then why can't we as well? And once again, what they were really talking about in this article is just that concept of the multiverse. One of the things we'll also see is we'll see that matter itself, such as the electron, and I'll show you a video, and it's been shown experimentally, that when I look at an electron, it will behave one way. When we don't look at the electron, it will go off and behave completely different, as though somehow it knows we're actually looking at it or not looking at it. But once again, these are some of the things that we'll address. Also, one of the things that will eventually happen is eventually I will invite the class, if you would like to, it's completely optional, to come in during one of the cub periods. I have a video that kind of talks about quantum computing. It talks about teleportation and how they've actually been able to teleport very, very small things miles and miles down the road. And in the video, it talks about the fact that if we can teleport this very small thing, then in theory, we should be able to teleport larger things as well. And it talks about some of the implications that we need to occur in order for that process to play out. So eventually, I'll send out an email to all students that if they would like to take a look at the video, it's a fantastic video. Most students kind of enjoy it. But at the same time, it doesn't work with your schedule. It's completely fine. All right, here we go. So getting started here. So some of the things we got up here is, anybody know this cat right here?
Schrödinger's cat?
Absolutely. So we're going to talk eventually about Schrödinger's cat and some of the implications of Schrödinger's cat. One of the implications is the multiverse that comes out of that Schrödinger's cat. So here we go. What we're going to do is we're going to start from the beginning. We're going to go all the way back to the beginning and just talk about the development of the atom and where the parts within inside the atoms are located. And then we'll also talk about what's known as the quantum mechanical model, which is the model that we use currently. So going way, way, way back to the original concept of this atom. Remember, we had John Dalton. He was the first person who actually got accredited with discovering this concept of the atom. And remember, you had Democritus who said the exact same thing, but John Dalton did the experiment, so once again, he's getting the credit for it. And the way that John Dalton saw the atom is he simply said, hey, this thing is like some indivisible particle. So if I go smaller and smaller and smaller, we'll reach something that's going to be indivisible. But once again, during his time frame, the technology wasn't there, but eventually as the technology caught up, they started to discover that, hey, this model is not right because we have these subatomic particles such as the protons, electrons, and also neutrons. And remember, there was this famous individual who actually was responsible for discovering the electron. Does anybody recall who that was? So first semester? JJ. It was J.J. Thomson. And remember, J.J. Thomson was pretty famous. Hey, I discovered the electron. And if you remember, one of the ways in which he described the actual atom once they started finding these particles is he looked down at his dessert. And remember, he said, hey, this plum pudding is the way in which I envision the atom is going to actually end up looking in this case. Where he said, hey, the pudding is going to end up representing the protons. So it's like a smear of these protons. And then we got the raisins dispersed throughout the pudding, which is going to represent our electrons. Now, once again, this is crazy, it was ludicrous, but hey, this is what he proposed. And at that moment in time, people were like, hey, he's pretty smart. Maybe that is what it looks like. However, there was this experiment performed by Rutherford. And he actually was like, for this experiment, I gotta make sure I choose this team here. What did he choose?
Gold.
The gold team for the gold foil experiment, because he needed to show that once again, well, let's go this route. When he went into the experiment, he thought this model was correct. And if you remember, when it came to the gold foil experiment, what he was doing is he was taking this really massive alpha particle. And he was like, hey, this is a thin piece of gold foil, like a pudding once again. If I shoot this heavy, massive alpha particle, it should just slice right through it. An electron bounce it out the way. Remember, his analogy was like, hey, if I shoot a cannonball at tissue paper, of course it's gonna slice right through it. But once again, to Rutherford's surprise, that didn't necessarily happen. And what Rutherford was actually able to deduce, based upon his experiment, is that the atom has a nucleus. And that nucleus is gonna end up housing our protons and also our neutrons. And one thing that we know about the nucleus is when it has the protons and the neutrons in there, it's going to end up having, in this case, a net positive charge here. So that's going to be like these positive protons in there. Neutrons have no charge. Then we got our electrons, and he simply said, based upon this nuclear model, that the electrons are kind of just hanging out there. Yeah, just kind of hanging out. But if we think about this nuclear model, something just doesn't make sense here. I understand protons and neutrons are here. What I don't seem to understand, these electrons just hanging out. What's wrong with the electrons just kind of just hanging out? Hey, I'm just hanging out here. What's inherently flawed with that? I mean, they're just hanging out. Does anybody see it? Nobody sees it. Hey, positively charged nucleus, electrons are just negative. I'm hanging out here. Alex.
Not in the shells.
Oh, you're going too advanced. Remember Rutherford, he doesn't know about these shells yet. We're gonna get there. But what's wrong? Why could somebody eventually say, I don't know about this?
They attract each other?
Absolutely. Why wouldn't these electrons just go crashing right into the nucleus? It's analogous to me simply taking a magnet and putting a magnet right here, and then putting a little bit of iron going around it. Of course, the iron metal is going to get pulled right into the magnet. So they knew that there's got to be some sort of explanation for what's going on with the electrons. Can't just be hanging out there. And that's when we're going to go into Niels Bohr's model. And this is the model that most of you kind of learned in your middle school. And what Niels Bohr did is he simply based his model on observations. He looked at the way in which planets orbit the sun. One thing that we know about the sun is the reason why the planets orbit the sun is because the sun has the most what? Gravity. And its gravity is due to its what? Mass. So because it has the most mass, it has the strongest gravity. And once again, the sun is like, hey, I'm pulling these planets in towards me. But technically, The planets are not falling into the sun because I remember in conceptual physics that they will not fall in, completely in, so long as they have some special type of velocity that I believe starts, look at that,
Terminal velocity.
not terminal, close,
Oh, I was gonna say like inertia.
no,
Centripetal.
that's close.
Tangent.
Tangential velocity, that's the term that I was looking for. Remember, it has enough tangential velocity, then it's gonna go fast enough that it's not gonna fall completely in this case, to the nucleus. Now, do not write that tangential velocity down. That's so conceptual physics. Only thing I want you to realize is that so long as they have this certain velocity here, then they're just gonna continue to orbit around the nucleus, just like, once again, the planets orbit around the sun in this case. Here we go. We got the planetary model. Energy levels. This is a new term that we kind of got here. Energy levels are simply going to be like orbits. They're where you're going to end up finding the electrons if you go looking for them. So you'll notice that, hey, we've got all of these different sort of energy levels where if I want to go find the electron, that's where it's at, on an energy level. Now, one of the things we're going to see here is we're going to use this N as a symbol to represent energy levels. So I don't have to write it out. I'm going to show you how I'm going to use it in 1 second. So if we look at it, we got our nucleus, we got our electrons, and then we also have our orbitals / energy levels sitting right here. Now, this is not the type of model that you traditionally saw in middle school. This model is kind of showing it how Bohr kind of envisioned it, three-dimensional. Now, a lot of times what we'll do is we'll take the three-dimensional model and we'll just simply make it into a flat Stanley sort of model where we're living in a two-dimensional world. It still works. Because even if I wanted to say, hey, this is really three-dimensional, we'll take this energy level right here and maybe rotate it out this way. It's still, once again, nothing more than a sphere that's kind of going around that nucleus. One of the things you'll notice is, look right here. That's my first energy level. How do I know it? Because it says right there, N equals 1. Remember, it said N represents the energy level. And the reason why we like the N is, one, I don't have to write down energy level 1. I can say N equals 1. Or I can say, hey, you know what? The electron happens to be in the N equals 5. No, I'm simply saying it happens to be the 5th energy level. 1, 2, 3, 4, 5. Oh, that's where the electrons can be found in this case. Now, Niels Bohr said that when it came to the electron has to exist on a given energy level. So it cannot exist in between, it must be on a given energy level, which means that the electron's energy, and also kind of how far away it is from the nucleus, is said to be quantized. And let me explain exactly what it means. Sounds like a very sophisticated term, but it's pretty straightforward and easy when you look at it. Quantized simply means I'm going to kind of restrict its value, or kind of like its magnitude in this case. And to give you an example of something that is quantized, we've got this stick man that's sitting right here. This stick man's potential energy is quantized. Because one thing I remember is potential energy is equal to, if I'm not mistaken, mass times gravity times, what's the last component here? That's it, exactly. Mass times gravity times height. That's potential energy. Well, we're talking about the stick man here. Then his mass, we're going to say, is going to be constant, and also the gravity is going to be constant as well. So really what's going to determine what his potential energy is going to be is going to be his height. So if I look at the stick man, and we're going to say the ground is here, going from here to here. If I look at the height that he is at the very top of the stairs, I can say he has a certain amount of potential energy. I can have the stick man go down to the next stair. And based upon this height, he has a certain amount of potential energy. He can get the stuff down to the next one. But one of the things you'll know is he doesn't just have any amount of potential energy. His potential energies are being restricted by the actual stairs. I can say that his potential energy is quantized. Because what he cannot do is he can't somehow levitate between the stairs and say, hey, I can get to any potential energy I want. Now, if I wanted to ensure that his energy wasn't quantized, or his height wasn't quantized, I could do something like this. Put a ramp. If I put a ramp, he can go to any height he wants to, which means he can exist at any potential energy he wants to. So the only thing we're simply saying here is that the electrons are quantized. The electron can exist on this energy level, it can exist on this energy level, it can exist on any of the energy levels here. But where it cannot exist is in between the energy levels. So it must be on an energy level. And once again, we simply say the electron is quantized. If we want an electron to actually promote from one energy level up to a higher energy level. So say this is the first energy level right here, and here's my electron sitting right there. If I wanted to go maybe up to the fourth energy level, then I've got to give it what we call in chemistry a quantum. And a quantum is going to be some energy that will provide it to allow the electron to jump from here to one of the given energy levels. So if I give it energy to make it jump up to one of the higher energy levels, we just simply call that a quantum. We will study this energy a little bit later on in the chapter. But for right now, just realize, hey, if we want it to go up, we got to give it a quantum. If you look at it, if you give the electron too much energy or too little, it is not going to promote up to a higher energy level. And what I mean by that is if I gave the electron enough energy to go to maybe right there, say it was right there, the electron's going to be like, no, I will not accept you. I will let that energy pass me by. I'm going to stay right here. And the reason why is, if you remember, we said the electron is quantized. It can only exist on these given energy levels. It cannot exist in between, so it will not accept. If it is not the exact amount of energy to get it to one of the energy levels, it's not going to accept it. Now you might say, that sounds a little strange, Mr. Ellison. But if you think about it, I can demonstrate this concept by using this glass right here. Has anybody ever seen a video where if you hit the glass with just the right frequency of your voice, that the glass will actually shatter? And some of you have, some of you haven't. If you haven't, once again, watch a YouTube video. They'll show it where they'll have somebody, they might be singing, and if they hit this at just the right frequency, the glass will shatter. And basically what's going on here is in conceptual physics, I can't remember your teachers, we got there last year, but there's this thing known as a natural resonance frequency, which means that matter has like this natural frequency. And if you can hit it with that actual frequency, then what it will start to do is it will start to go into a wave. So the glass will do is if I can hit it with just the right frequency, right now it's just like, hey, I'm just vibrating here because I'm a solid vibrate. Oh, you hit me with the right frequency. Oh, I'm gonna start doing this right here. And the problem with glass is as you start making the glass do this, that glass is very rigid. It's like, I can't do that. I can, but I'm gonna cause the glass to actually shatter. So one of the things that I have been trained to do is I have been trained with my vocal cords to actually hit the glass with the right frequency, which means I can make this glass actually shatter. So I'm gonna see what I can do here. Okay, I think I'm ready. Here we go. That's the best that's gonna happen. It's not gonna happen here. I do not have the vocals to be able to break this glass. But once again, if you watch the YouTube video, you'll see somebody, because if I'm here, the glass is like, you can't sing. I'm ignoring you. It's like I'm still not accepting that frequency in this case. It's not until you hit it with just the right amount of energy that it will accept it and start doing the wave. The same thing is true with the electron. You don't give me the right amount of energy, I'm just letting that energy pass me right on by in this case. Which leads us to something that is interesting here. We have just hit something that is going to be like, wait a second, how is that possible? If you really think about what I just told you, the electron has to exist on one of the energy levels sitting here, and it cannot exist in between. Why is this kind of like perplexing? Because it's analogous to me saying, hey, this classroom's an energy level. Across the hallway in Mr. Griggs' classroom, that's another energy level. Over in Berkman's Hall, hey, we got another classroom, that's another energy level. Guess what? I cannot walk through those hallways there. But the problem, if I go and I jump, like I run and I leap, do I not exist in between at that point in time as I'm flying through the air? And I'm probably going to end up going like maybe 1 feet with my long jump, so I'm not even getting close there in that case. I'm still, once again, I'm existing in that region, which means that we can't do this. That defies, once again, what we said, that the electron is quantized, which means what does the electron do? The electron takes what is considered to be a quantum leap, where it leaps from one location to another without existing between the two locations. So, to show you this kind of as an animation, wait a second, make sure my volume is turned up here. Perfect, it is up, and I gotta turn it up here as well. Here we go. And this is actually a snippet of that movie that I was telling you we would be watching. Well, the optional movie if you'd like to come in and watch. Here we go.
Quantum leap so surprising is that the electron goes directly from here to there, seemingly without moving through the space in between. It was as if Mars suddenly popped from its own orbit out to Jupiter. Bohr argued that the quantum leap arises from a fundamental...
And that's enough of Bohr for right now. Once again, those who come and watch the actual video, you'll hear a little about some of the rationale. But when it comes to this world of quantum, there are things that, once again, that are occurring that we don't really understand how. Like, eventually when you watch that video, if you decide to come in, they're gonna have quantum physicists from Stanford, from MIT. Also, they have one from my great school of University of Maryland College Park, and they have these professors in there. They're just talking about some of the implications and some of the things that are going on with quantum. And one of the professors, I believe he's from MIT, was saying that if somebody tells you that they know exactly what's going on here, they're lying to you. And this is a professor from MIT saying that we still don't understand some of these things. We don't understand why or how the electron can simply go from here to here without actually existing between the actual regions. There's a lot that we are still learning when it comes to these things such as quantum. And once again, when you come and you watch the video, if you do decide to, you'll learn a little bit about string theory and how string theory works, and technically how if I have an electron that's here, I can entangle it with another electron. So once again, how this entanglement occurs and what it means. It simply means that, hey, if I have one electron, best I can do this, say this is an electron here. And say that it's maybe rotating clockwise, the other one's rotating counterclockwise. Then I can entangle them to where, hey, this one's gotta be turning one way, this one's gotta be turning the opposite way. As soon as I turn this one the opposite way, this one turns the other way. I can take these two electrons, they'll be discussed in the video as well. You can move them infinitely far away from each other. So I can move it all the way out to Pluto. As soon as I turn this one way, this one will turn instantly the other way. But the interesting thing about it, once again, I'm trying to throw this out there, just trying to get more people to come in, maybe watch it. Some people are like, hey, well, maybe this one's sending a message to this one right here. But there's a problem there. Because the fastest thing that we know that can move, the fastest moving thing happens to be what? Light. In order for this to go from here all the way to Pluto, you're talking about still some time. It is instantaneous. As soon as I turn this one's turning. Speed of light couldn't even get there fast enough in order for that to occur. Which brings up, once again, some interesting things that will be talked about or discussed in the video. So once again, I'm just trying to put some little things out there, little, what do we call those things? Little crumbs, I guess, to have you possibly come in and watch the video. All right, so we got this quantum leap here. Continuing on. A couple of things that we're going to see here is this first statement. That's pretty straightforward. It simply says that as we take an electron and we put it in these higher energy levels, that of course the electrons can be further from the nucleus, which, I mean, clearly if we go back here and we look at right here, if I take an electron and put it in the first energy level, hey, you're a little bit closer to the nucleus. If I go all the way to the seventh energy level, you're further away from the nucleus. So as they go higher and higher in these energy levels, they're further away from the nucleus. Also, we simply say that as the electrons go higher in energy, on the energy levels, they're also going to be higher in energy in this case. And that's kind of important, because one of the things that we're going to see eventually is we're going to see that when I'm going the wrong way. There we go. As we go, or as we start placing electrons into these actual energy levels, one of the things that I know is I know electrons are a form of matter, and I know matter always seek out lowest possible what? Potential energy. So it always seeks out lowest possible energy, which means that as we start to place electrons eventually into the atom, we're going to say, hey, electrons, where do you want to go? They're going to say, oh, I'm going to go to first energy level, your lowest in energy. And then eventually, as we fill the first energy, a no vacancy sign will go up, and then we'll go to second, and then we'll go to third. So we'll kind of build this from the ground floor on up in this case. Give you an example. When you go off and you're a senior, you graduate, you got into your great college, and then it's got to come to dorm selection. And the dorm selection is a big thing for college students. Guess which floor you want to be on? The first floor. Yes, you do. If not the first, you don't want to go too much higher. Because when you got to move in and you got all that stuff, you got to move all the way to the fourth floor, that's a lot of work. Or, hey, you know what? I'm on the fourth floor. I run downstairs. Oh, man, I forgot my calculator. Let me go back up all these flights of stairs. You want to be in lowest possible potential energy in this case. Lowest floor. Same thing with the electrons. All right, one other thing to point out. Unlike the actual rungs of a ladder, the energy levels are going to get closer and closer together as we go higher and higher up. Well, right now, just accept it. But eventually we're going to see that there is an implication that's going to come out of this as these things get closer and closer together. Something's going to occur here, and we'll address it eventually. All right, this slide I'm skipping over because we just watched that video. And we're
Quantum leaps up.
There we go. Now, with Niels Bohr, his model was spot on for hydrogen. Beautiful. Worked out nicely. Did all these experiments. And experiments were like, yes, 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 everything is working. So Niels Bohr was like, this is fantastic. I think I struck Eureka. And if you think about it, the reason why he went with hydrogen is because hydrogen happens to be the simplest element. Anytime you come up with some sort of model, you always start with the simplest thing you throw at it. And then you go more complicated. Once he moved past a uni-electron atom, and he went to a multi-electron atom, such as helium, that's second one on the periodic table, things just fell apart. Did not work in this case. Now, the great thing about Niels Bohr is Niels Bohr was like, hey, you know what? Clearly I'm onto something. It works for hydrogen, it seems to fail. And a lot of times when you have these sort of experiments, you don't say, hey, you know what? Let's just get rid of the whole entire thing. No, let's work on this thing. Let's see if somehow we can get and modify this thing to where it will actually work. And the next person who actually came about to really figure things out, and this is where every teacher's dream happens to be, Niels Bohr was a professor. He taught a young student by the name of Schrödinger. 10 years after Niels Bohr had proposed this, his student came along and came up with the actual current model that we have right now. And we're going to see that when it comes to what is known as a quantum mechanical model, we're going to see that this model, a lot of things are going to carry over. There will be something that's going to be different that helps to kind of explain why Niels Bohr's model actually fell apart. But Schrödinger, what he did, Schrödinger, is he came up with what is known as a Schrödinger's equation, which looks like this thing right here. Hamiltonian operator times wave function equals the energy times wave function. Don't worry about it. It starts off right here. But then really quickly, it goes to this. And then this thing just grows and grows and grows. And keep in mind, in order to work in this realm of understanding what Erwin Schrödinger was actually able to do, you gotta have a lot of calculus here. So if you want to be a chemistry major, you're gonna need Calc 1, 2, 3, you'll need differential equations, linear algebra, you'll need advanced. There's a lot of math going into this actual concept. Now, this is the really fantastic thing that I have to say. is a lot of times I have students, I'll be like, oh man, why do I have to learn this math? When am I ever use this math? How am I going to use it? Well, early Schrödinger, everything we know about the electron was not discovered experimentally. It was derived via mathematics. So he was able to figure out what the actual energy levels looked like, how much energy the electrons had, all that stuff he did via mathematics. Then after he came up with all the math to explain what was going on with the electrons, they went into the experiments. And the experiments confirmed that his math was correct. That's how powerful mathematics happens to be. A lot of things that we know about nature is once again derived via mathematics. We talked about, who was it? We talked about Newton, right? Did we ever talk about Newton in the math? No? No? Yes? What do we say Newton was responsible for coming up with? Exactly, calculus. So there's so much that goes on. And once again, even those who might come with me in the AP next year, even though calculus is not required, we'll get to this thing known as integrated rate law. Integration is a form of calculus. And those who are in the calculus will go through and I'll kind of derive these equations. Those who are not in calculus, they're like, I just see all this stuff going on, these little wiggly lines, the derivatives and all that good stuff. But I like to show you how the math can come into play to help us, once again, derive different equations here. Now, once you solve the actual equation for the wave function square, then a lot of information came out of it, such as, hey, where the electrons will be located, how much energy do they have, what's the shape that they'll take on when they produce their path, and what's the orientation. And you're like, what are you talking about, Mr. Harrelson? What I'm talking about is when it comes to this slide, what I expect for you to know based on this slide is this right here and this right here. I'm not going to ask you, hey, what is Schrödinger's equation? I can't work with it right now. I'm not going to ask you what the wave function square happens to be. What the Hamiltonian operator is not important. Now, because we don't understand necessarily all the math implications, what we're going to do is we're going to kind of be on the surface of quantum. We're not going to go deep into it, but just kind of look at it from the surface perspective. Now, the interesting thing is I had one student who came in actually last year, and she was a former student. And we talked about quantum in this class, also AP, but she went off to college. She came back. She's actually going to the grad school, and she's doing what is called quantum encryption, which means that she has to know all of this mathematics that actually goes into this new sort of encryption that's actually taking place with this quantum encryption. So maybe somebody else in the class might decide to do something. And quantum encryption, whether you realize it or not, that is big time. That is where you're going to have different militaries and governments that would want to actually hire you to actually encrypt their actual data. Because if you go quantum encryption, then you're talking about things that are higher, much higher level of encryption. And a lot of times when we have very, very sensitive data, we don't want a traditional encryption. We want something such as quantum encryption. All right, here we go. Let's look at some of the things that are actually similar between Niels Bohr's model, planetary model, and also the quantum mechanical model. They both have energy levels in them. So where are the electrons to be located? Oh, on these energy levels. What else do they have in common? The electrons are quantized. They exist at very specific energies in this case. Also, the electrons, if they want to promote out, they got to take a quantum of energy in. Also, they got the quantum leap. Hey, I disappear from one location, reappear in the other location. Also, the energy levels are getting closer as we go higher and higher, just like I showed you that picture there. Now, the difference between the two is Niels Bohr simply said that, hey, if you want to go find the electron, where is it going to be found? Hey, on this circular orbit here, or maybe this circular orbit here. It's going to be on one of these circular orbits. Well, when it came to the quantum mechanical model, he did his mathematics. He was able to figure out that, that's not the case here. The case is that the actual orbitals are a lot more complicated than simply being a basic circular orbit going on here. We're going to see that, hey, we got spheres that they can make. Where he said, hey, it was kind of like this two-dimensional space, just a circle here. He's saying, no, it could be three-dimensional. It could be anywhere on that sphere. Or maybe the electron can make paths that produce all these other shapes out here. And we're going to take a look at each one of these shapes and kind of make sure that we understand what's going on here. But there's a lot of things that are going on here that is completely different in this case from Neil Bohr. Now, really quick, I'm going to say this quickly. You're not responsible for knowing it. Just want to point out why Neil Bohr kind of was okay with hydrogen in this case. If you think about hydrogen, hydrogen is going to have its electrons. It only has one electron. Where's that one electron going to sit? It's going to sit right there on this little circular orbit here. But when you come to the quantum mechanical model, one of the things we're going to see is that the first electron is going to go on this sphere right here. And if it's on the sphere, then hey, the electron will be on this surface. But at the same time, if it goes this way, it's still the exact same distance from the nucleus, regardless of where it is on that sphere. It's like me taking this circle and then just taking it and just turning it around. It's the same distance, and that's kind of why his model worked. The problem is once you start going to multi-electrons, you got to start introducing these things that are going on here as well. Not responsible for knowing that, just kind of pointing out what's going on. All right, this picture right here. I've got these puzzle pieces that are sitting here. And the reason why I put these puzzle pieces sitting right here is as we move forward, you are going to be a little bit lost here. And what I mean by that is the analogy I like to give is if I were to simply take a box of puzzles, without showing you the lid, I just dump them all on the table, you're going to be like, wow, I have no idea what that image is going to make in this case. The same thing is about to happen here. I have dumped some pieces on the actual table. What I'm going to do is I'm going to start taking a piece and add it into another piece. But you're not going to see the full picture until we get to a certain point tomorrow. We're not going to make it here today, but tomorrow. Once you see the full picture, you're going to be like, oh, I see how all these puzzle pieces fit together to produce that image in this case. And the reason why I like to show this is when I first started teaching the notes for this part of the actual chapter, as soon as I go to each slide, oh, I got a question, well, how does that relate? Oh, how does that relate? And the problem is that you will not see how they relate until you see all the pieces come together. So what I'm going to say is that if you have a question as I move through these notes now, just write it down. Just jot it down. Once I show you the full picture, and hopefully that eureka moment's going to go off, like I see how all these pieces come together, then if you still don't see it, once I tell you, hey, you should see the full picture, then ask that question. But 9 times out of 10, you're going to probably see it once you see the full picture, and it'll kind of address the questions that you have. All right, how much time do we have here? We got 4 minutes here. So I'm going to probably make it through this slide, and then we'll probably stop, and we'll just pick up here tomorrow. So really quickly, atomic orbitals and orbitals. You're going to hear me use these things interchangeably. And when I talk about the atomic orbitals, it's going to be the path in which the electron is going to take. There we go. When it comes to the actual path the electron can take, there are 4 different sort of shapes the electron can make when it takes a specific type of path in this case. And what they decided to do for the actual different shapes that the electrons can make is they decided to use letters in this case. So we're going to see eventually that, hey, the electron can make a path that produces an S-shaped orbital. Or maybe it can produce a path that's going to make a P-shaped orbital, or a D-shape, or an F. And we're going to look at each one of these orbitals tomorrow and see what they kind of look like in this case. The only thing I need you to know from this slide is, hey, S are lower in energy, P's are higher, D's are higher than F. Which simply means that if the electron is given the choice, it's going to say, hey, I want to produce this S orbital. Oh, I can't produce the S, or I'll produce the P. If I can't produce the P, I'll produce the D. And the last worst case scenario is I'll produce the F orbitals here. All right, I'm going to stop here. Tomorrow, I'm going to come right back into the notes. We're going to go through this part really quickly once again, and we're going to start looking at these orbitals, and then I'm hoping, keep my fingers crossed, that we'll get to a point where you'll understand exactly how those pieces are put together. But one thing just to point out, homework for tonight. In a second, I can't remember if I put it up on Veracross yet. I know I have for the other section. It's on Veracross. So you're going to go into Shobi, and you're just going to answer those multiple choice questions. They go exactly with the notes. So for this sort of homework assignment, I'm holding to a higher standard. So you should be getting, when I say all of them right, I'm looking like 80 to 85% of the questions right, because they're coming directly from your notes. If there's anything that would, hey, you had to solve problems, and I'll be like, hey, it's your first time, you're prone to make mistakes. Just look at your notes. The answer is sitting there. All right, I will see you mañana.